Alrighty, so, oh right, how do I check that again? There we go. Alrighty, so looks like that's functioning then. Guess I'll move over to the right one. Managing windows when it's one screen can be real helpful, but also it'll be I'll have to flip back and forth to be able to see what's on in the chat. So if responses are slow or something, that's why. So we're gonna start off symbolic logic, and I've made a list of. Wait, why did the screen go black? No. Oh, that's why. Okay, I think I figured it out. It's because I minimized the thing. Okay, that's fine. It's fine. I fixed it. So we're gonna start off with atomic sentences. Basically, this is gonna go until, I don't know, around 8. And we'll see where we've gotten at that point, and have another lesson at some point. It'll be a fun time, that sort of deal. So we're going to start off with atomic sentences and like examples, and feel free to just keep messaging in chat to like participate in all that. The first bit's going to be a lot of talking and explaining, and when we get to the symbols, that's when I'll actually use the screen part, you know. So symbolic logic, the purpose is to take sentences, and the overall goal is to take sentences and things, or arguments in daily life, put them in symbols, and prove them so that beyond a shadow of a doubt they are correct. There's inductive logic and deductive logic, and this is deductive, where no matter what, you are right. If given the premises are true, the conclusion must be true. That's the goal of symbolic logic. To do that, though, you need to know how to write out the premises and conclusion, and then how to do logical proofs. And to write out the sentences in symbols, you need to assign letters to what's called an atomic sentence of that overall compound sentence. It's the simplest form of it. So let's say, for example, Lucille likes pie, and I'm saying this because I have a coconut cream pie right next to me that I will be eating shortly. Lucille likes pie. You could symbolize that with L for Lucille, or like P for pie, and so that the atomic sentence for that would be P. Or you could do an if-then statement. If Lucille likes pie, then Lucille will eat pie. And you could do, like, I don't know, L for liking pie, and then the symbol for then, which I'll go into shortly, and then P for like pie, or E for eating, whatever you want, as long as you know what it is, as long as it's consistent, and as long as you don't use it twice. Now, this does get a little more complicated later on, but we're not going to worry about that yet. Essentially, later on, the way that you represent atomic sentences will change depending on if there's a subject, but that's not a problem right now, because we're in essentially start simple, then get more complicated. It'll be fine. So I guess, are there any questions about atomic sentences? Because if not, then we can just keep continuing with that. I don't know how much of a lag there is on the stream, but either way, if there aren't, then I guess we can go through the symbols. Okay, then we can go through the symbols, and that really helps connect atomic sentences. They're really important. So let me pull up this list that I have on the side. I was trying to find my notes from the class that I took earlier, and I couldn't find them. I think that I left them back, like, not in my dorm room, so I just don't have them with me. But first we're going to up the brush width. So this is actually, that's a pretty big brush width. Okay, yeah, no, I'm changing this. That's not working. It's too big a brush width. Maybe 10? Yeah, this will work. So you have a symbol that looks like this, and it is if the first part, then the second part. Yeah, it's literally if then. Then you've got this, which is, it's just a dot in the middle of the page, and that is and. So both A and that says and please. Oh, I know what'll make writing better. One sec, I'm gonna get my mouse, and then I will have handwriting that is possibly acceptable. One struggle bus of writing anything on Paint.net with a trackpad is it's a trackpad, so that's gonna be difficult. All right, back in a bit. Alrighty, so we're gonna try this again, and with hopefully better handwriting. So you've got if, if the sentence is if A, then B, assuming that A and B are atomic sentences, or examples of atomic sentences, then you would symbolize this with A, then B, because, yeah, so if A, then B. And so the next one is A and B would end up being written as A and B. Then if it's A or B, it would be, it looks like a V, which is real easy. It's or, so essentially it could go that way or that way. But here's the thing, this is inclusive or. Inclusive or. And the inclusive or means a lot of the time in English it's not specified if it's inclusive or exclusive or. And inclusive or means it can be A, it can be B, or it can be both. Exclusive or means it can either be A or it can be B. But for the purposes of symbolic logic, if you're interpreting it as as inclusive or, it can be A or it can be B or it can be both, then you use this symbol. It's more complicated if you want to do like exclusive or. Let me zoom this out a bit so that you can see the whole thing, and maybe like write them down if you need to. So those are the basic symbols. There's one more complicated one with this, where it goes both ways. So if A then B if A then B, and if B then A, would be A and then 3 lines. So kind of like an equal sign, but with 3 lines. So kind of like equals B. So if you have A, then you must have B. Actually, that's a better way of putting it. I'm going to erase this because that's better. Oh no, oh no, oh no, I've made a horrible mistake. What have I done? What have I done? Here we go. It's A-okay, my dudes. Everything is fine. It is all fine. Back to 10. Or rather, that's also A if and only if B. Would also be that. So if and only if B, or if A is true, then B must also be true. That kind of thing, where they necessitate each other. If A, then B. If B, then A. If it goes both ways, then that's what that symbol is. Alright, gotta check the chat. Just the thing about lag. Okay. So, let me check to make sure I'm not missing symbols, first off. Oh, there's one other that's real important, which is this is not. So it's the negation symbol. Let me see if I can write this more cleanly, and like it neat. It's that little tilde thing, right above the tab button, where it's shift in the key right above tab, and that's a tilde, and it's used to negate, it's used as a negation. So let's say instead of Lucille likes pie being your atomic sentence represented by L, I'm pretty sure I can do layers. Yes, layer 2. Let's do another layer here. Alrighty, so layer 2 here is going to be a bit of an example time, I guess. So let's say you have L likes pie, and you represent that with, I don't know, let's do L for liking pie. And then you have the sentence L does not like pie. If you wanted to make L does not like pie its own atomic sentence, that wouldn't work because there is a does not in there. And so what that would have to be is negation L for it is not the case that L likes pie. Essentially, if you can arrange the sentence in a way where you can start it with it is not the case and then have a simpler sentence, that means you do negation in whatever that simpler sentence is. And so that's that one. What's next on the list of things? That's propositional logic, negation, material implication. Then material equivalence, implication, conjunction, inclusive, exclusive. Tautology. And we're not doing quantifications yet, so. Alright, yeah, so I guess that means we can move on to basic proofs with symbols. Or we could always do like basic translations. I don't know, do you have a particular preference between going and translating sentences into, oh no, I need to, okay. Between translating sentences into into symbols, or translating sentences into symbols, or why can't I think of the other thing? Or going through and connecting symbols so that it can show how logical proofs work. Because I'm not sure which would be best to start with. It depends on if you care more for already starting with application, or yeah, translation makes sense. So okay, in which case connections it is. Why is, oh, right. Okay, so for connections, let's go ahead and start with some really simple argument. How about we start with, continuing on with the food stuff because there's food here. Let's start with, L likes pie. L likes pie. These are our premises. So premise 1, L likes pie. Premise 2, if L eats pie, they won't be hungry. And then 3, if L likes pie, L will eat pie. So to symbolize these, let's image canvas size. Let's add another. Oh no, what have I done? Where's it gone? Hello? Aha! Here we are. Layers. What a confusing but helpful thing. Alright, so translating these, we can have, let's change color. Let's go blue. So sentence 1 can just be L. L likes pie. 2 can be if L eats pie, so E, then they won't be hungry. So that's a negation. Negation H. And then if L likes pie, L will eat pie. So L, then E. And so this is how we start the proof. That's 1, 2, and 3. Oh, I also get to teach you how to cite your proofs. And so once we have this translation, we don't need that first part anymore. We can just ignore it. It doesn't matter. In fact, let's get this. Move you over here, a bit farther away. No, why? Oh, because, okay. So, okay, yeah. Because I need that to be on a different layer than it was. I forgot I was still on the same layer. Layer 4, here we go. So, rewriting this out somewhere that's fine anyways. So 1L, 2 E, then not H, 3 L, then E, and the conclusion is not H. So L is not hungry. That is the conclusion. Also, one thing about symbolic logic that is interesting in my opinion is that it doesn't matter if your proofs are if your premises are accurate, so long as the logic actually works. So it doesn't matter that it's not true that if L likes pie, then L will necessarily eat pie. There are things that could get in the way of that. It's assuming the premises are true, then the conclusion must be true, which is the case for this. So we start off, and we know we're trying to get to that conclusion. We're trying to get to the conclusion, not H. And this is a relatively simple one, so you can kind of fill in the dots, where you know you have L, and usually that's a good place to start. Where can you plug that in? You can plug that into 3, and then you plug it into 3 and you get E, and when you get E, you get not H. But to actually write it out is a bit different. You have to cite the steps that you write it out under. Technically, this part would not be in the actual proof. It would actually, I need to move this because that's not where it would be. I am remembering these things as I'm writing them out just because it's been like a semester, so that would be there. And you also do a slash to, no. You do a slash to show like that's the conclusion, and just erase this part. I think so. I'm not 100% sure. I'm pretty sure it's slash and then not H shows that not H is what you want to get. And so, step 4, because we have L, and that's the only solid thing we have, you go and say E. So you have E, because of, so here it's, this is a conditional statement. It's called conditional. And so you go over to the side here where the explanation for like how it is that you arrived at E, and you go conditional, and then E for elimination. So conditional elimination, and you eliminated the conditional by plugging in L, which is in step 1, so step 1, and then comma, and you plugged it into 3, so 3. So conditional elimination, step 1 and 3, and that's how you got it. And then for step 5 here, so you have E, so you're going to get not H, and that gets you where you want to go, but you still have to prove it. You still have to go like, no, I'm citing my sources. Here's me citing my sources. And so it's once again conditional elimination, but this time instead of step 1 and 3, it's step 4 and 2, or you can write 2 and 4, whichever you prefer. It doesn't really matter as long as you cite it, because you're plugging 4 into 2 or 2 into 4 if you want to go numerical order. Either way, and that's how you arrive at not H, and that's an example of a proof. A relatively simple one, but still. So yeah. I think, I guess any questions really? And wait a half a minute for the lag to catch up. I'm pretty sure I know why they do that in case people do gaming stuff. And so you don't want it to have that impact games, especially live ones. So yeah, that's like the whole situation with that. Yeah. I feel like this one's pretty straightforward. It gets really complicated really quickly, but this is a pretty straightforward one. At least a straightforward example, and you can apply this into actual logic if you know that if it's, Oh, it's called elimination because you're eliminating the step in between. Essentially, because you are, let's go for red this time. Because you're eliminating this, you're taking that out. By plugging L into there, you're taking out that and getting E. So you're eliminating this part, and that's why it's an elimination. If it's for an introduction, which can happen, so let's say if I wanted to continue on more steps here, I could. Let's say instead of not H, I wanted not H and L. Currently, I technically have those, but they're in 2 different steps. And so I can't say that I have that until I have it. And so it would be conjunction introduction with steps 1 and 5, because I'm combining step 1 and step 5 to be not H and L. And so it's elimination when you're getting rid of it, and introduction when you're adding one in. So any questions about that? Like, elimination versus introduction versus whatnots and the different symbols and things? Alrighty. So, that's proof steps, proof examples from basic sentences. Example basic translations. This is actually going a lot faster than I thought. So, I don't want to overcomplicate this quite yet. That can be like, I don't know, next week when I can be a bit more prepared or something. But we can do practice from like example arguments. The only thing is those arguments do have to be deductive, and they can also be nonsensical arguments. So that can be a fun thing to sort of do. Where let's say, okay, let's scroll somewhere else here. Let's come up with some weird argument, something that does not make a lot of sense. And one thing that I haven't mentioned yet, actually, which is important. With this here, if I wanted to add E, because clearly, like, you can just add E with another conjunction introduction here. You can't just have not H and L and E. You have to put parentheses, because you can only have 2 things together at once. And let's say you wanted to get L out of that, you would have to take E out first, and then you could take the parentheses down, and then you could get L, but not before that. It's really complicated. It's complicated in that, like, why couldn't you just do it? But it's not complicated in that you need to show every single step. And if you do not show every single tiny little step, then it does not count as a valid proof. And so that's like the main thing there. Every single tiny step matters. And if you skip them, then it's not valid. Oh, wait, no, I need to erase. There we go. It's a bit strict in that way, but that also helps later on when it gets complicated. I'll see if I can find some good examples, and sort of like write those out, give them to y'all. Actually, let's see if I can find some. Symbolic Logic. Oh, what's it? Proof. Well, let's do problems. Symbolic Logic problems, images, because worksheets are fun. Basic statement equivalent, no. Distribution, equivalent. Reduction. Rules of implication, rules of replacement. Oh yeah, that's a thing too. Modus ponens, modus tollens, hypothetical syllogism, disjunctive syllogism, all that. Okay, so there's a few other rules to introduce, but I think I'll probably put that on a document and share that at some point. Let's start with I'm not sure if I should go over the rules of implication and rules of replacement first, or if I should keep giving a few more examples. For the most part, this is pretty straightforward here. So I feel like before continuing on forward, it is important to do rules of implication. So let's go ahead and do that then. So this isn't going to be proof time. This is going to be like more rules time. First one is, those ones make sense. That one's fine. That one's fine. P then Q and R then S then P or R and P. Oh yeah. Well, no, that's also fine because you can do that with an if then. Simplification. Okay, here's a good example one. So this is going to be technically a proof example, but it's also going to be literally working out one of the rules of implication, which is called the Constructive Dilemma, which the way that I was taught, you don't just like cite the kind of rule of implication. You literally go through the proof of it, and so it is, for example, P then Q and R then S. So that's your first premise. Second premise is P or R, and the conclusion is Q or S. And clearly this is true, right? So if you have P or R, and if P then Q and R then S, then you have Q or S, right? Well, how to prove it, though? That's the main question. And that can be a pretty difficult thing here. And so what you do is you start something where you do this one long line going down because you don't know how long it's going to take, and you start what is called a subproof premise, abbreviated SPP, subproof premise, where essentially you're going, if this, then the end, then the ending thing is true. So if you have P, and then you continue on down and do the, assuming this, and then you come to a conclusion, and then you come to another conclusion, and depending on if and essentially because of 2 being here, and it's, you know what, I think I'll just show you, and that might help. So we're going to do 4 is going to be conjunction elimination line 1. You only have to cite that one line because you're only eliminating it from the first one. So P then Q. And then 5 will be conditional elimination line 4. And, well, why is that so messy? Line 4 and line 3. And so you get Q. And so now you have Q, but only within the subproof premise. You don't have anything to take it out of that subproof premise yet. And so we're going to make another one. Because, you know, why not complicate things, right? No, not really. And so we're going to do, this is another subproof premise. And it assumes R. So let's say you have R. And so bring this down a bit. And we're going to do conjunction elimination on line 1, and that'll give us R. That's messy. That'll give us R, then S. I think that's what it was, right? R then S. Yeah, R then S. And so if you have R then S under this subproof premise, then 8, you can do conditional elimination and get S. And now, step 9, you can take it out of the subproof premise and go, okay, so what I got from that is Q or S, and what's it? How do you cite that? I I don't remember the exact citation of it. Hold on, I'm gonna see if I can find it. What was it? I'll find it at some point. I'll find it one of these days, but I don't remember. It's got to be something. It has to be something. I just don't remember what it is. Well, that's okay. Struggle buses are fine. We'll figure it out eventually. And so, Q or S is true, and you cite, oh, wait. No. Okay, so, that's not... I'm trying to think through, like, what would it be, because it's going to be it's going to be an elimination or an introduction of something, because those are the kinds of citations you have here. And this is, it's disjunction introduction. That's what it is. Disjunction introduction. And you cite line 2, because that's where you're getting the P or R. And then you cite 3 through 5. It's literally 3-5. And then you cite 6-8. And that's your proof. And that's how you prove Q or S. Because you go, okay, well, I have either P or R. So if I had P, then I would have Q. And it's that or R. And if I have R, then I have S. And therefore, I have Q or S. And you cite it disjunction introduction with line 2, 3 through 5, and 6 through 8. There we go. I remembered. So yeah, that's a fun time. Okay, I was kind of concerned there. I was like, why can't I remember this? So that's disjunction introduction, which tends to happen in subproof premises. Yeah. And so that's technically called the constructive dilemma, but we don't care about that. We just care about being able to prove it, since proving it is what matters. And being able to prove it with the very simple, like, whatever it is that you need to prove, you will be able to prove with, like, disjunction introduction, disjunction being the or statement, conjunction introduction, or, like, introduction or elimination, conjunction introduction or elimination, conjunction being and, or, I forgot what it's called again, the if-then statement, introduction or elimination. Those are going to be your proofs. That's always how it was in my symbolic logic class from start to finish. It was always that's how you prove it. And this is a really fascinating thing in my personal opinion, that no matter what, if it is deductive, then you can prove that without a shadow of a doubt this thing is true, given that the premises are true, with 6 simple, like, citations. So, I don't know, I really liked that. You can't cite 2 through 8 because you need to show what steps were taken, and you need to split it up in that particular way. So essentially you cite 2 to go, well, that's where I started with the thing, and then you cite 3 through 5 to go, this is my first subproof premise, and 6 through 8 for that's my second subproof premise. You can't cite, you can't combine things once they're in subproof premises, because those are like their own little separate, like, micro universes, kind of. It's like in the universe where this happens, then it's like, okay, so in the AU where P is true, this happens, and so you can't combine AUs, and so you need to cite them differently. And I don't 100% understand it, but I know that's how it works, and so that's all I'll say for now. I'll look into why, but that's all I'll say for now. You can't combine your alternate universes. And so, let's see, that's that one. We could go into Demorgan's law. That's something that's used a decent bit. Or Demorgan's rule, whatever. Essentially, Demorgan's rule is, if not P and Q, what's it? Wait, what is that symbol? Hold on. That does not follow. One sec, I'm trying to read something, and let's just Demorgan's law. Yeah, Boolean logic. It's A and B. Then, sorry, this is also kind of like refreshing me on what things have. Yeah, sorry, the chat lags, so sometimes it's like, oh, well, time for creative metaphors. So, negation operator. Oh, and then both ways. And so I guess that's the biconditional. Oh, that's the word for it. Conditional. Conditional is the word for it. I need to write these down somewhere. There's conditional, biconditional, disjunction and conjunction, and negation. Those are the 5 basic ones. I should write these down, so I will. New layer. Yay. Because otherwise I'm absolutely going to forget again. So, conditional. That one's conditional. Biconditional. Then negation. Conjunction. Disjunction. Oh my gosh, can you imagine if I included this into into my little like the little note thing where it's like, oh yes, well, here are some secret alphabets that you need to figure out, and I just include symbolic logic symbols and like have fun as like part of the structures of the sentences. Oh, how about we just make a new language? How about that? Just, oh no, we have so much difficulty already with languages that exist and we can look it up on Google. Japanese, Google Translate works well with very specific languages, but badly on many, many others. So
it's like good for Spanish.
Yeah, it's good for Spanish. Kind of Latin. Is it? No, not Latin. Okay, not Japanese. It's awful with Japanese. All that. Oh, that was a bit of a tangent. That's okay. We can go on a bit of a tangent. Okay, tangent time. All right. Did you like the Tulin or what's it? Tulin Vaki thing? I'm not exactly sure how to say it, but the oh yes, well, one or more. Good on German, really, really bad on Finnish. Yeah. I saw the thing about like the characters just being like Pokemon, and it's like, well, that sure is an interesting way to put it. And I guess would you consider that like this is the bad end result of putting 2 Pokemon in the same Pokeball? That's what this is. That's all in all. That's what the drama with that character is. Oh man. Forcing 2 Pokemon into the same Pokeball, it doesn't, like, they're not gonna like it. It's not gonna go well, and so clearly you need to do some crazy like nonsense with magical artifacts with that. And so like obviously that's the source of all of the problems with my entire character nonsense. This isn't going to make any sense for people that just like, for anyone that comes across this going like, oh, symbolic logic, yeah, I'll go check that out. Symbolic logic help, great. And it's like, what Pokemon, what? It's going to evolve into an uncooked plant spike and turn. Oh yeah, clearly. And it makes sense because like the badges for like dueling, like, whoa, it all connects. It's a big conspiracy. Not really. Disclaimer, I have no idea. No, I don't think so. Maybe, I don't know. I need to do my research on those creatures now, because I saw that people have been plotting to do some character stuff, and I'm like, oh joy. Well, I need to be prepared. So, all right. So that honestly seems like a pretty good place to end this now. How long has this been going on for? Like, 45 minutes of symbolic logic. That's pretty fair to start off with. And honestly, with this amount, you can apply it. I'll try and do more prep work for the next lesson. I'll probably be able to do next week on Saturday as well. And so I'll just, call it Symbolic Logic Lessons 2, and that'll be part 2. So, yeah, hope to see you then. I should know how to end streams by now.